For section 8.1, we look into the periodic table just a little bit further, and looking back at each of our element squares, we should notice that you have your element symbol, you have your element name, and then you also have a mass on the table. So you have one that's a whole number, and this represents the number of protons. Then we have another number that looks like this. So what we need to talk about in this section, in the next couple of sections, is why is this number a decimal? Why is it not a whole number like the number of protons? So remember, the number of protons is a very definite thing. We can't have half of a proton. But this number is a little bit different. And this is the mass that we're going to be referring to throughout this chapter. So the first thing we want to look at in section 8.1 is to understand the concept of average mass and explore how counting can be done by weighing. So remember, the big idea here is that atoms are really, really small. And if atoms are really, really small, then we have to be able to represent the large numbers of atoms that we represent in a certain sample. So for example, if we have 12 grams of carbon, that's a lot of atoms of carbon. So we need a way to represent how many atoms we have and to bridge that to something that's tangible, something that we can actually take the mass of and see in a laboratory. For section 8.1, we want to start by investigating the concept of an average. So if I ask you to take the average of these three numbers, an average is simply the total value of the items divided by the number of items. So if we're counting the average or calculating the average of the numbers 3, 4, and 5, then we're going to add 3 and 4 and 5, and then divide by the number of times a number appears, or the number of items we have. And in this case, we can see that we have 3 items. So we're dividing this by 3. That's making the assumption that all of these values contribute equally to the total, that one of these has a value of 3, one of them has a value of 4, and one of them has a value of 5. That's why in an average, we are dividing by the total number. We're assuming that they all contribute equally to the total. So if we carry out this calculation, we see 3 plus 4 plus 5 is 12. We divide that by 3, and we get an average value for these three numbers of 4. So we can explore this idea of averages when we talk about counting by weighing. So take jelly beans, for example. You don't go to a candy store and ask for 100 jelly beans. Everybody knows that's going to be a pain to count out 100 jelly beans, and either you're going to be doing it or the clerk is going to be doing it, but there's just it's way too complicated to count out 100. Instead, we count by weighing. So if we know the approximate mass of 100 jelly beans, then we can do this much faster by saying, I'll take a pound of jelly beans rather than 100. So average masses make counting by weighing possible. If we know the average mass of one jelly bean, then we can calculate the mass that 100 jelly beans would weigh, and then just do a quick measuring of an amount of jelly beans in terms of mass rather than counting them out one at a time. So if we're saying that one jelly bean is approximately equal to 5 grams. Now, those of you who are a little bit familiar with gram measurements are probably noticing that 5 grams is going to be a little bit high for a jelly bean, but we're just using it as an example to get us started. So we're assuming that many jelly beans have been massed and that the average mass of those jelly beans is 5 grams. So remember, it's not going to apply to each and every jelly bean. But this is just a way for us to say, okay, on average, a jelly bean weighs 5 grams. So sometimes I may get more than 5 grams, sometimes slightly less. So we want to know what is going to be the mass of 100 jelly beans. And remember, this is so we can say, I'll take this many grams rather than counting out 100. So we say that one jelly bean equals 5 grams. And again, remember, this is just an equivalent statement. And an equivalent statement gives us 2 conversion factors. So we're either talking about 1 jelly bean over 5 grams, or we're talking about 5 grams over 1 jelly bean. And which one we use depends on where we're coming from. In this case, we're coming from 100 jelly beans and converting 2 grams. So we see that jelly beans is on top, jelly beans is on the bottom. Those units are going to end up canceling each other out, which is what we want. And what we can do here now is multiply across the top. So we have 100 times 5. We can divide by what's on the bottom, but that's just a 1. So we can ignore any 1s when we're plugging numbers in for conversion factors. So 100 times 5 is 500 grams, which makes sense in terms of our problem. Because if each jelly bean weighs 5 grams and I want 100, it makes sense that we have to multiply that value by 100 to be able to determine the mass of 100 jelly beans. Now, how many jelly beans are in 26 grams? So we are going to start by writing down what we know and our equivalent statement. So this kind of guides us how to set up our problem. So we're going to start with 26 grams. This is our given piece of information. Remember, conversion factors are used to calculate. They are not given pieces of information, and we don't start from those. So 26 grams, we draw our line. We know our gram unit will go on the bottom because we want that gram to cancel. And we know 5 is paired with grams. So 5 grams on the bottom, 1 jelly bean on the top. This time we have a number in the denominator and we can ignore that 1. So the math that we're doing here, remember, is 26 times 1 divided by 5. So what we get here is 5.2 jelly beans. The only problem with this number is we can't get 5.2 jelly beans. Nobody is going to take a knife and cut 1/5 of a jelly bean. So instead, we would say how many jelly beans are in 26 grams. We can't have just 5 jelly beans because in that case, it's not going to be quite 26 grams. So here we would have to round up. So context is important. We have to be able to put whole jelly beans in there. So I know that 5.2 jelly beans equals 26 grams, but I know in order to get 26 grams, I would need more like 5 jelly beans in this case. And does it make sense looking at the math? Yeah, it makes sense. 1 jelly bean is 5 grams. So if I'm looking for nearly 5 times that many, I'm going to need 5 times that number of jelly beans. Why is counting by weighing important to us? For the same reasons I mentioned earlier. We want to make it simpler. We don't want to count out multiple things, especially when those things that we're counting are in very, very large quantities. And like we said, atoms are tiny. So as chemists, we need an easy way to count a lot of things. So we don't want to use numbers on the order of 10 to the 23rd like you're going to see happening with these atoms. We want to be weighing out much closer to the number that you see on the periodic table, 12 grams of carbon, for example, instead of counting the individual atoms, which could take a very, very, very long time. So in 8.2, the next thing we want to talk about is looking at the idea of being able to take an average mass to count something. We want to know how we apply that to chemistry, or what does average mass mean in terms of how we use it in chemistry. So for 8.2, our aim is to understand atomic mass and its experimental determination. So what we want to look at here is what an isotope is. And you may have heard this term in physics before, but we need to know that isotopes are atoms of the same element with different masses. So how does that work? Remember, elements are made of, we have a nucleus, and then we have electrons, which orbit the nucleus, move around the outside. So what we need to remember is what's inside a nucleus. So inside a nucleus, we have protons and neutrons, and this is what gives atoms their mass. Electrons have a small amount of mass, but it's negligible, which means it's so small compared to the mass of a proton and a neutron that we don't even count it. So what we want to look at to determine the mass of an element is its number of protons and neutrons. So each of these that you see down below are examples of isotopes. They are the same element with different numbers of neutrons. So we know, according to the periodic table, that carbon has 6 protons. So this will never change. This number tells us what element we're looking at, and the element we're looking at tells us what number we're going to find on the bottom. This number on top is the number of neutrons plus protons. So what we're able to do now is determine how many neutrons are in each of these isotopes by simply subtracting the top number from the bottom. So we can see 11 minus 6, and this will give us 5 neutrons. In the next one, 12 minus 6 gives us 6 neutrons, and so on, 7 and 8. So you can see now if each proton and neutron contributes a certain number of mass to an element, then we know that if those number of neutrons are changing a little bit, then the mass of each of these isotopes will be changing a little bit. So up until now, we've been talking about averages in terms of each part of that average contributing equally to the overall total. So you've just been able to divide an average, a total number, by how many of those items are there. So in this case, what you might think we would do to determine an average mass is to count 11 plus 12 plus 13 plus 14, and then divide this by 4. This does not work in this case, and it does not work because each of these isotopes do not contribute equally to the total. So I'm going to stop right here, and I'm going to put in another video that shows you an example of how to calculate an average atomic mass of an isotope. And this will be really all we're looking at for section 8.2 is how average atomic masses are calculated. The one thing I want you to remember here, because a lot of students have this as a misconception when they're approaching this, is we cannot calculate average in the regular way because each of these isotopes do not contribute equally to the total. We have isotopes that are occurring naturally in different abundances. In other words, I may have 90% carbon-12 and then just a mix of all of the other isotopes. So that's why we have to take into account average atomic mass in terms of isotopes, because each isotope does not contribute equally to the total. They contribute in different amounts. So watch the video, and then that's the end of your first set of notes for today.